everyone. So last video we talked about how machine learning solves the equations. Before that we talked about vectors and matrices, but there is a question I completely ignored. Where do vectors actually live? And surprisingly, answering that question leads us to one of the most important ideas in machine learning, and that's vector spaces. So to give you a recap, uh, we have studied vector, then we studied matrix, then we studied system of equations, right? So far we have treated vectors as objects that we can manipulate, add them, scale them, use them to represent the data, but we haven't talked about the environment that they exist in. So vectors need a home. And that's where vector spaces come. It's the space where vector lives. Simple. So, to formalize it, let me introduce you to what we call a group. So, group. Now, what is group? So, group is a set of elements and an operation defined on these elements that keeps the structure of the set intact. So, we have few elements. So, we have few elements, and we have an operation which is defined on these elements. That is, if I do any operation that involves the elements of suppose a particular set A, then the structure of the set, that is, uh, the elements of the set will remain intact. I mean, it won't happen that a new element will come, or a new element of which does not belong to that group comes in, or some element goes out. Okay, it won't happen. The structure of the set, that is the set that it is, it will be as it is. I mean, it won't change. So groups, I don't know whether you might have heard this or not, but it's a very crucial topic. I mean, it is important in computer science, cryptography, coding, graphics, everything. So, okay, let me tell you exactly what a group is in a great detail. So, like, consider a set G and an operation. Actually, it's called the tensor product. So, if I can define G gives G. So it is basically that the operation this, which is done on G and G, it will give G only. Okay. So now to be classified as a group, it has to pass by certain rules. I mean, it should check whether it is satisfying the rules or not. Okay. And there are like mainly four rules. If it satisfies all those four rules, then it will be called as group. And there's another fifth rule, which if it checks, it will be called as abelian group. So I'll just tell you what are the 4 points to be called as a group. So first is we check the closure. So we check the closure of G under any operation. Suppose this. So I'll define it as like for all x and y which belongs to G such that x, the operation y, belongs to G. Second will be the associative property. So associativity. So it tells that for all x, y, and z which belongs to G such that x, or the operation y, and z equals to x, the operation y, z. Third is it should have a neutral element. So what is a neutral element? I'll just show you. So there exists an E which belongs to G, and for all x which belongs to G, there exists an x which when operated on like with the neutral element E, it gives us x, and similarly when E is operated with x, it still gives us x. So like if I talk about addition, so in addition our E will be 0 because anything which is added to 0 will get the element itself, right? If I talk about multiplication, our E will be 1. So the E will be defined based on the operation, this, right? So the fourth is the inverse element. The group must also have an inverse element, which is for all x which belongs to G, there exists a Y which also belongs to G, such that X operated by on Y gives E, or similarly Y, the operation X gives E. So, if I talk about addition, my E will be 0 because suppose I have 2. The inverse of 2 in addition is minus 2, which is 0. If I talk about multiplication, my E will be 1 because X will have an inverse of 1 by X. So inverse doesn't mean that it's always reciprocal. Inverse is defined on the operation. So only when the operation is multiplication, then only we define inverse as the reciprocal of the element. So that's why inverse doesn't mean always the reciprocal, right? So we can show inverse as inverse. So inverse of X equals to X inverse. Okay, so again I'm telling, this does not mean 1 by X. It will mean 1 by X only when the operation is multiplication. So it's operation specific. Now, so if something follows all these 4 properties, it will be called as group. Now the 5th property is the commutative property. Commutative property, which is suppose X operation Y, then it's equals to Y operation X. So if this property also holds true, then we call the group as the abelian group. So abelian group is just a special type of group which follows the commutative property. Now if I give you example, suppose Z plus. So in this, my the group is the set is Z, the integers, and the operation that I'm working on is addition. So let's check whether Z plus follows everything. Z plus is closure. So any integer added to another integer will always result in the integer, right? So this holds true. Associative. For integers, associativity is true. Neutral element. So for addition, our neutral element was 0. And integers have 0? Yes, they have. So yeah. And inverse element, for addition, the inverse element is, suppose if I have the A, then inverse element will be negative A. So for integers, they both are present, hence inverse element is also there. Commutative, inverse are also commutative. So yeah, so this is a group, and that too an abelian group. Now if I talk about natural numbers including 0 and I do plus in them, so everything you will see that it's there, but one thing is not there, which is the inverse element. In natural elements, we don't have the negative numbers, right? So just because inverse element does not exist, it isn't a group. Then Z, and I do with multiplication. So Z has integers, but for inverse element of a multiplication, it's 1 by Z, and integers don't have fractions. So the inverse element is not there, hence this is also not a group. And yeah, so like there are many more examples that you can see it online, or you can solve that in any book. So that's what a group is about. Then if I talk about general linear group. So what's a general linear group? So a set of regular invertible matrices, that is a matrix whose inverse exists. So so matrix A, which belongs to our cross n-dimensional matrix, it will be called a group with respect to matrix multiplication. So suppose we take a matrix this and we define it as matmul. Okay, so with respect to matrix multiplication, we call it general linear group. Okay, so when we take a matrix A and define it on matmul, so that's what we call a general linear group. And as you know that A dot B is not equal to B dot A if A and B both are matrix, right? So it's not abelian, it's just a group. Okay, and that group with respect to matrix multiplication and matrix, that's what we call the general linear group. So with this knowledge, let's deep dive into vector spaces. So earlier the operation were inner products on the G, right? So G cross G gives G. Now in addition to the inner operation, we also have an outer operation, okay, which we'll define like suppose Z plus and this, right? So this will be called as inner operation, and this will be called as outer operation. outer operation. So basically you can treat this as addition and you can treat this as the scaling, right? Because vectors, addition and scaling are the two major properties that defines a vector. So if I take a vector space V, so the vector space is a set of two operations. So V plus and this, which means that if I have plus, then V cross V gives V. If I have this, R cross V gives V. So here, in this thing, what we have is when V is denoted plus, this should be abelian. Second, so this was the first. Second is the distributive property. Distributive. So for all lambda, which belongs to R, and then x comma y, which belongs to V, there exists lambda into x plus y, which is equal to lambda x plus lambda y. Okay, one more is that for all lambda and phi, which belongs to R, psi, and x belongs to V, so lambda plus psi, x equals to lambda x plus psi x. So this is the distributive property. Third, associative, which is the outer operation. So for all lambda and psi, which belongs to R, x belongs to V, so there exists lambda psi dot x equals to lambda psi x. And fourth is the neutral element. Neutral element with respect to outer operation. So for all x which belongs to this, such that 1 dot x equals to x. So these are the four things that is needed for a vector space to exist. So all x which belongs to the vector space V are called vectors. So we have just now defined a vector space, and anything x that lies inside this vector space V are called as vectors. So this is a much more formal definition, because remember the two things that we used to call vectors as vector was one was the addition and one was the scaling, which is multiplication. And this is what we are doing in the vector space. We are having V, we are adding them and we are scaling them. So these three things define a vector space. So the neutral element of V on addition is 0, as I told you that that V plus E equals to V, and so E will be 0, the neutral element. And in vector, how we define the neutral element, it is like this: 0, 0, 0 transpose. Basically it's like this: 0. This is the neutral element. Then the elements lambda, which belongs to R, right? They are called scalars. Lambda is a constant, so they help in scaling during a dot product. So they are called scalars. And the outer operation, which is this is the outer operation. So the outer operation is called multiplication by scaling. Okay, that's why I called it scaling. Multiplication by scalars, so scaling. Also, there's one thing to note, and that's multiplying two vectors. One second. Two vectors as just AB is not defined in the standard linear algebra. Why? Because vectors are usually treated as matrices with dimensions, right? And matrix multiplication only works with the same dimensions, right? Where the dimensions are compatible. So now the two standard vector multiplication, first is the outer product, and second is the inner product, which is also called as a scalar or dot product. So outer product, what we do AB transpose, which belongs to R n cross n, in which A equals to n cross 1 and B equals to 1 cross n. And in inner product, we have A transpose B, which belongs to R. Okay, so you can remember is that the outer is we transpose the outer thing, which is B, and the inner is we transpose the A. Okay, so you can remember like that. So if I give you an example, if I have a vector space V which is n-dimensional and n is a natural number, so in addition, if I do x plus y, okay, So basically x1 x2 till xn plus y1 y2 till yn. What I'll get is x1 plus y1 x2 plus y2 till xn plus yn. And if I talk about multiplication by scalar, and scalar is my lambda, so what I'll get is lambda x, which will be equal to, lambda x1 x2 till xn. So lambda x1 lambda x2 till lambda xn. This is what we get, and in this lambda belongs to R and x is n-dimensional. And suppose if my vector space is m cross n dimensional, where m and n, which belongs to natural number. So in addition, a plus b, what we'll have is like a11 plus b11 till a1 n plus b1n, am1 plus bm1, amn plus bmn. So it's defined element wise, and if I do the scaling, what I get is lambda a11. This is what I'll get after scaling. So now let's talk about vector subspaces. Vector subspaces is just like what we have subsets. So vector subspace is just basically a set of vectors which is contained in the original subspace, in the original vector space. So it's a set of the original vector space, that's why we are calling it subspace. So you can just think of it as a subset of the vector space. This is subspace. So when we perform operation on elements, it stays within this. Okay. So just like when we defined vector space, that whatever operation we perform on the elements of vector space, it stays within that vector space. Again, whatever operation we perform on the vector subspace, it will stay in that vector subspace only. So to bring things in, to talk about things algebraically, let's define a vector space V as this multiply, and we have U, which is a subset of V, and U is not a phi, it's not an empty set. Then U on U plus this is a vector subspace of V, because U is a subset of V, right? U is a subset of V. Now U, and with U we have defined a new space, and that new space will then be called a subspace of V. Or subspace, you can also call it as linear subspace. Linear subspace. Also, the vector subspace U inherits properties from the vector space V, since it's just a subset. So all the properties of V, you will have the same properties. So, like, to determine if U this is a subspace of V, what we need to do is that first is that U is not an empty subset, and 0 is a part of U. So this is the first condition. Second is closure property of U, which is first is with respect to the outer operation. So for all lambda which belongs to R, for all x which belongs to U, such that lambda x belongs to U. Okay. Second, so outer operation was a multiplication. With respect to the inner operation, which was our addition, so for all x and y which belongs to U, such that x plus y belongs to U. Okay, so it should be in the same subspace. This is what we are calling it. So now let me give you a few examples. First is the trivial subspace. Trivial subspace of vector space V. So as you know, right, the trivial, suppose the trivial solution. Trivial solutions are generally all zeros. Similarly, the trivial subset, the trivial subspace or vector space V is this and the vector space itself. Just like just like in sets, we have a set will always have two sets, which is the set itself and the zero, right? The null element. So here also the trivial subspace are the same. Now, second, if like I ask you, I'll give you a few graphs and I'll ask you that is this a subspace? So first I have this, second I have this, third I have the two lines and the area between these two lines, and fourth I have the point here. Now this I won't call my subspace because if I take any 2 points, suppose this and this, and add them, then I get a third point here, right? So it is outside of our vector space V, hence we won't call it a subspace. Then here, as I told you that 0 must exist in subspace, and here 0 is out of this line, hence this is also not it. Now in this, again, the same thing that we found it here, that any element can come outside when we do any operation, so it's also not there. And this is it, because in this our only set is 0. So 0 has the outer operations, inner operations, and this condition. So yeah, this is a subspace. Then the solution set of our homogeneous equation, which is Ax equals to 0, is a subspace of Rn, because we have Ax1 equals to 0, Ax2 equals to 0, so Ax1 plus x2 will be equal to Ax1 plus Ax2, and since Ax1 Ax2 is 0, so we get it as 0, and A lambda x, which is basically just lambda Ax, we also get as 0. Hence we both are getting zeros, so the solution set of Ax equals to 0 is a subspace of Rn. Then next one point is that for any equation Ax equals to b, the solution set is non-homogeneous. What is meant by non-homogeneous? Homogeneous solution is when we get Ax equals to 0, right? But definitely it will be non-homogeneous since we are getting a b here, right? Then next is that intersection of subspaces is a subspace, right? We have a vector space V, we have a subspace A, we have a subspace B. Now the intersection of the two subspaces is a subspace, right? So it's a subspace of A, it's a subspace of B, and subspace of V. Okay. And lastly, every subspace here, which belongs to plus this, is the solution space of a homogeneous system of homogeneous linear equations Ax equals to 0 for x which equals to 1. Okay. So what this statement means is that every subspace can be described as a set of solutions to some homogeneous linear equation Ax equals to 0. So for example, if I take the line y equals to 2x in R2, which is the second dimensional, so it's a subspace and it can be written as 2x minus y equals to 0, which is of the form Ax equals to 0. So the statement means that any subspace is exactly the collection of vectors that satisfy some linear equations whose right hand side is 0. Okay? Yeah, so again, why ML cares? Because we have images, we have audio, we have text, we have embeddings. So all these are just vector representations. And again, where do vectors stays? In vector spaces. So machine learning loves vector spaces because almost everything eventually becomes a vector in machine learning. Like you have again the images, audio, text, embeddings, user behavior, sensory readings, everything, all represented inside the vector spaces. And why subspaces matter? So like this sounds abstract, but dimensionality reduction, PCA, embeddings, recommendation systems all rely on heavy subspaces. So the deeper I go into machine learning, the more I realize that vectors aren't just data structures, right? They are objects living inside carefully structured mathematical spaces. Again, now just continuing my previous lines, that vectors gave us data, matrices gave us data sets, systems of equations showed us how machine learning solves problems. And vector spaces shows that the mathematical universe where all this happens, what it is exactly, right? So next video, linear combinations and why almost everything in mathematical machine learning can be built from various vectors. Until then, goodbye.